So I was wondering the other day, what is the overhead of making a C function call from Go? And the reason you might be interested in this is that there's lots of great C libraries out there. And if you're making an engineering decision, you want to know what the cost of that is. So let's say that you're making a game and you're using Raylib or SDL. You need to know, it's like, okay, what's the cost of making this C function call? So that way I can design my program properly. So I created this benchmark, and I just wanted to go over it real quick and then show you the results that I got. So the idea behind this is I'm using this Pure Go library. And the reason for this is there's essentially two ways that you can make C calls from Go. You can use the foreign function interface that's built into Go, and that means that you end up having to use CGO, which means instead of using the normal Go compiler, you use I believe it's GCC. That has a GCC, Go compiler that will compile your Go code and then link it with the libraries, the C libraries that you want to use. And the other way is to use this Pure Go library. And the idea behind Pure Go is that you use the normal Go compiler, and then it will load dynamic libraries into your program, register the functions, and then call those functions. So it's like dynamic library loading instead of statically compiling them into your program. And so this is great. It's used for lots of things. There's actually a SQLite library that uses PureGo. EbitEngine, which PureGo is part of the EbitEngine project. EbitEngine uses PureGo. There's lots of other libraries. There's an SDL library that uses PureGo. So I wanted to test out PureGo because that's kind of the one that I use a lot. So the idea behind this is that I want to have a function, and I want to have a function in Go and then in C, and then I can benchmark the time of those two functions. And then if I compare the average time to run those functions, the time to actually do whatever the function is doing should be the same. So the difference between the two should be essentially the overhead of calling the C function. So what I decided to do was write a function that just adds two numbers. It's kind of the simplest, fastest thing that you can, well, not the fastest, but it's one of the simplest things that you can do. And so I decided to do this. So the Go function is just, return A plus B. And then I did the same thing for C. So I wrote a C program called add.c, and you can see that it's just adding two numbers and returning them. So that's the entire C program. You can compile this into a shared library, and I did. I compiled it into a shared library called libadd.so. And so that way, PureGo can load this library in at runtime and call the function. And that's exactly what happens here. So I'm using this. By the way, for CGO, what you do is you essentially create a variable that has this function pointer to it, and then you can fill that function pointer. I use this init function here. So basically in Go, if you're not familiar, an init function, there's an init function that you can create, one per package, and each package will first try, if it finds an init function, it will run that init function first, and then it will do its normal thing. So in order to do this testing, what I'm going to do is set up, my PureGo library, and then I can just run my normal benchmark. And so the idea here is that we'll just open the library and then just register the add function that we have. And then the benchmarks are very simple. So I'm using the built-in Go benchmarking facility. And so the idea is we'll just run a loop and call the Go function. And then, one thing I found out is that in order to prevent the Go compiler from just basically deleting the benchmark and optimizing everything away, you essentially want to do this to make sure that it keeps this variable around and it actually calls this Go addition. And of course, the same thing for the C function. C function does the same thing, except I just call the C function. Also, another thing I learned is up here, you want to use Go no inline. So this is a special comment that will tell the compiler not to inline this function. Otherwise, what it'll do is it'll just take A plus B, And instead of calling a function, it will just add those two numbers together. When I first ran this program, the additions seemed to be ridiculously fast. So I ended up doing this go no inline thing. So with that, I already ran the program because it takes around 12 seconds to run. And here are the results for my processor. It takes around 1 nanosecond to make this function call. So the function call, basically call the add function, add the two numbers, and then return that value. It takes approximately 1 nanosecond. Now for the C function, to do the same call, except from go to C, it adds the numbers, returns back, is around 220-ish nanoseconds per call. And so you can see that like a pure Go function has very little function call overhead. Well, actually, I didn't show you the overhead for the actual Go function, but you can see that the C function, calling a C function, has a fairly high overhead compared to a normal Go function call. So it's around 220 nanoseconds to call a function. Now, is that a lot? Well, it kind of depends on what you're doing. So 220 nanoseconds is a relatively small amount of time. But if you're, say, making 1 million of these calls, well, that adds up very quickly. And the time that it takes to do 1 million C function calls is going to be a lot. However, if you're only doing a few of these things, even like, let's say you're creating a game and you have 1,000 C function calls, right, that you do per frame. Well, 220 nanoseconds times 1,000 would be, what is that? 1,000. That's around 200. That would be 220 microseconds. And so even if you're running at 120 FPS, your budget is around 8 milliseconds. So this gives you, 220 microseconds is going to be a very small amount of your budget. So unless you're having a game where you're counting your microseconds and you really care, you most of the time don't even have to care, even if your game is running at 120 frames per second. So doing these things is actually, this is actually fairly fast. Now, if you're doing something, like I said, where you've got a hot loop and you're doing like 1 million of these calls, then it might matter. So that was basically all I wanted to cover. I just had a little bit of curiosity, and this also kind of goes into the idea of engineering something, right? So having curiosity about this and like measuring these things is important because as an engineer, you want to design things properly, right? You have requirements, and there perhaps are competing ways to do something, and this helps you, right? If you're knowledgeable about the field, then you can make better decisions. So that's just something I wanted to call. Oh, by the way, I guess this is obviously for my processor, which is a 7800X3D. The actual numbers for your processor might be different. And actually, another interesting thing would be to check the overhead of an actual Go function call. And we can do that actually really quickly. If we open this up and take away this go no inline and run this, we can actually see that the function call, instead of it, well, it's not a function call anymore because Go is able to inline this. So if we don't have a function call, if we just add two numbers together, that takes approximately, 0.2 to 0.23 nanoseconds. So if you think about it, like let's say it's just 0.2 nanoseconds, that means we could do 5 additions in a single nanosecond. That's pretty crazy compared to 1 addition for if we have a function call. So that means that this 1 minus 0.2, that means it's approximately 0.8 nanoseconds for the overhead of a function call in Go. So 0.8 nanoseconds. That's less than what I thought it would be. I thought it would probably be, well, I don't know. I thought it would actually be more than that, but 0.8 nanoseconds is actually pretty good. But that gives us kind of the real measurement then, that the overhead for a Go function call is 0.8 nanoseconds on this processor approximately. And then the C function call is approximately, 220-ish nanoseconds. So so that's it. And have a great day, and till next time.